And that'll include the current chapter we're working on. So we'll get the homework. I'm gonna have that posted today, I promise, and then we'll be doing a quiz and whatnot. But so everything up to then, that'll be all included on the final. This last chapter we won't have on the final, but I do want to review it. The thing with going into filters is, I mean, we can analyze and see their properties. You know, what makes a filter, and that type of thing. As far as like practicality is concerned, like what are we going to do with them? That actually comes more into play in the next class, 134, the first solid state class, where I mean, as far as like what you do with filters, they have a lot of applications for media communications, broadcasting and whatnot on specific frequencies, but but they also have an effect with, and this is more practical for us, right? Is how they work with power supplies and what you do with them. I mean, they even use, they'll be using like filtering effects and diodes and whatnot for like VFDs, drives for motors and whatnot. And you'll start getting more into that like in the later classes as well with 150. But as far as like seeing actual effects, well, this for filters, we actually start playing with that in 134. So I'd like to review it just to introduce it to you guys, so that way when you do get to 134, it's not like an extra thing that you have to go through. I mean, you'd have to review as and whatnot, but that would be about it. So with that, so this will be a semi-short presentation, if you will. Hold on here. Let us pull this up. Go. Go. All right. I know we're so excited. Right? Look at that. Oh, chapter 23, filters. So we're just going to take a look, see what these are about. I mean, some of the stuff that we were touching on so far with the resonance and getting used to ideas of frequencies and whatnot, and the ways that RLC circuits can impact frequencies kind of ties in with this. We won't look at the last half. We'll just cover basically what filters are at this point, just like a little introductory, if you will. And here we go. So the way they measure it is like this. It's basic. Of course, everything we do is, it's measured with one thing versus another. And now frequency response, or what were of interest as far as filters go. I think we're having trouble connecting, huh? But so we look at our voltage gain versus our frequency, and that's something, see, we haven't gotten into that as well yet, and that's something we get more into in solid state. We'll start looking at voltage gain, amplification effects, if you will. We start looking at things like that with transistors and operational amplifiers, and start looking into voltage gains and what that's all about. So like I say, this is sort of like a prelude to getting into solid state, which would be the next section. Actually, of this, you still use the same textbook, which is a good thing. But these are the 5 types of filters that you would run into out there. And in a certain case, they're, with a few introductory things here, these kind of become self-explanatory, if you will. What they call a low pass, a high pass, a band pass, a band stop, and an all pass. Now, these are all applicable to, like I say, for communications effects. So you have to think in terms of frequencies, and I'm desiring specific frequencies. I don't want crossovers, I don't want unwanted frequencies. If I'm doing low frequency signals. I don't want high frequency signals coming in there and interrupting things, that it doesn't come out well. Usually it just, it's basically, it's distortion. You get unwanted things through, and it's affecting your original signal. So it's distorting it, if you will. So really what we look at is what a filter is capable of. Now, when we were looking through before, okay, we're looking through the resonance circuits, and we seen that a certain center frequency was very allowable, and we had our max power at that range, and et cetera, et cetera. It's like even to the point where we had like a little, little elbow room where we had like an upper frequency and a lower frequency, okay, and we are totally operable within that range. And then anything outside of that, the power goes to, and our signal is attenuated to the point where it has no amplitude or very, very little amplitude. So little impact, if you will. So with that in mind, we look at what we call a band pass. And within that range there, what they do is within that range that is set for, those frequencies are allowed to go through. And the reason that you would have a filter for this type of thing, so think of it, I mean, think of it more like we're broadcasting radio, okay? So we got the radio waves coming through, and they're totally susceptible. They can get unwanted interference from the outside, different signals crossing over and whatnot, even to the point of our receiving end, our radio and antenna, what they're receiving. Well, we don't want that stuff because it's garbage as far as what we're concerned with, right? We want the original signal. We want that radio transmission, and we want it nice and audible, clear. So with the passband, what happens is we set up a certain allowable set of frequencies, and it'll accept those. And then anything outside that range would be called the stop band, in which case it's literally rejected. It's not allowed to come through. We don't want that signal. We don't want the distortion or the noise or anything like that. So with that in mind, this is how we kind of view these things, and especially, ideal response is always ideal. So a very, very popular one, a low pass filter. And what they mean by that is it's low pass. It allows, basically, as you see here, his definition, right? All frequencies from 0 to the cutoff frequency, which would be a low one. We could even say we'd be down in like the hertz ranges and stuff like that. And then anything up and over that range that we've set, based on the values of our components, is literally rejected. It'll block all frequencies. They're just not allowed to come through. And then you get a brief region, okay? Because of course, if you set it allowable, we got components in there. They're not ideal. We're looking at the ideal model, but they're not ideal. So there is a small transition point from where we accept to where we don't accept. So with that, you have a slight chance of there still being a little bit of distortion only within that particular range. And then there's ways to alleviate that as well. But in ideal world, the low pass filter would have a 0 attenuation and signal loss in the pass band, and infinite attenuation in the stop band, and it would just be boom, and that would be it, and it would work beautifully. Well, reality kicks in, and it does not quite work that way. Oh, hold on here. What is going on? Hold on a second. I think Gavin's having a hard time connecting in here. Oh, good Lord. I'm not so good on the connection ends of these things. Anyway, but But ideally, that's what we'd be looking at, right? Your cutoff frequency here would be perfect and super sharp transition. And so everything up and above would be allowable. Anything down and below would be rejected. And it would just work like magic. Well, it doesn't always work that way, but we're looking at the ideal response. The high pass filter, same concept, just the other side of the coin. Now we're interested in allowing like high frequencies to come through and rejecting low frequencies. Because we don't, you usually, when you do these things, you don't want crossover distortion or anything like that. Interferes with your signals. And yeah, they had to go through trial and error back in the day. Of course, back then we just had the AM band at that point, right? So it was a bit easier for them, but this is the reverse side of the coin. We look at it, I mean, essentially the same concept. We will allow all frequencies over the cutoff frequency and reject anything under. Ideally, it'll have infinite attenuation. And we're all clear what attenuation means, right? We kind of seen that effect with the lab yesterday, where when we were at like the ideal frequency for that particular circuit, you had full voltage magnitude, okay? But as you started to wander or drift away from what that center frequency was, right? And we got up to the point, even to the point of our bandwidth, we started to see the voltage amplitude drop down. And then as it goes further and further out, okay, to the frequencies that we really don't want, you would see that that voltage amplitude started to basically get attenuated down, and to the point where if the frequency were high or low enough from the circuit, that the voltage magnitude was virtually zero. That effect is attenuation, where you dampen a signal down to the point where it's unusable. You just don't have enough magnitude to actually do anything with, right? Then that would be an attenuated signal. It's literally like you started with an original signal. And if we analyzed it, there would still be a signal per se there. It's just we wouldn't be able to do anything with that. But that's typically what they mean by attenuation, where, yeah, you get signal squashing. And he likes to, of course, we always, with doing these, we look at the ideal models. We can even state like, okay, here's our bandwidth, what we would like to allow through from this frequency to this frequency. We would like to allow anything to go through, and then anything outside of that range, we don't want it. And so we basically attenuate those signals so they can't have anything to, interfere with. And then we allow these original ones to go through. And basically the models here, we're going to look at the different types. So the band stop is an interesting one. Now, this is like the reverse side of the coin, where anything between these two frequencies is rejected and anything below or above is allowable. So if we were like, say we knew that this particular frequency was always going to interject a signal into our signal, and it was an unwanted effect, we could set up a band stop circuit to literally reject anything within that frequency range, and that would just eliminate that signal from interfering with us altogether. Like I say, we're just going to look at the models here and take a peek at it. Just kind of a little introduction to get your gears going. Yes, from some such simple little circuits as the resistor, capacitor, and inductor, we can do this. And these filters are essentially fairly simple circuits. As far as componentry is concerned, there's not a whole lot to them or anything. And we use them widely. Basically, and saying communications in a way is a wrong thing for me, because it's not just in communications, basically in anything where you have a signal transmission, these would be acceptable. That even includes in power transmission, because you have to think about that. In power transmission, I'm still essentially transmitting a signal, right? I've got AC signal coming at you. So it has a sinusoidal response. And so with that, I can have, noise aberrations and whatnot involved in my power transmission, which could also interfere with certain things that may or may not be beneficial to me. So if I were finding that I was getting crossover or some type of distortion on my power lines and whatnot, I could set up filters to alleviate that and get rid of those aberrations so they wouldn't mess with my original signal. You can get certain spikes and whatnot. And if they have a duration effect, like on your power transmission lines, it could even be enough to cause breakers to trip and machines to malfunction and things along that line. So filtering effects isn't just for communications ends. It's basically any application where we have a sinusoidal or even other types of, nonlinear type signals, okay, but that are susceptible to noise or interference from outside signals, we can very much use filters to alleviate that effect. Um, they're nice to use. They're passive. The parts generally aren't that expensive, which is a good thing. Even the big, I mean, comparatively, like the really large capacitors and the really large inductors, if you will, yes, they are going to be a bit more in price than what you have in your lab kit, right? But all in all, if we look at how much like our power transmission equipment is overall, and then we add in this stuff to it, the cost is very minimal. And that's times when you'll see, um, they even have like certain engineers that work for Ameren and such that come out and look at your signal transmissions, for your power lines and whatnot coming into your building. And they will at times add filters. And that's why you'll see these like that one resistor I'm finally handing out in the lab where it's got that gigantic heat sink on it. Yeah, you'll start dealing with componentry much like that. Anyway, so and this is probably one of the most popular of all the filter circuits. It's called an all pass filter. And you may ask, all right, what the heck is the point of an all pass? Because it is exactly what the name implies. It will pass all frequencies. Now, a good thing for something like that is in the case of signal reproduction, if you were trying to, let's see, I don't know, maybe your signal quality might be something that isn't desirable on your receipt of it, but you have enough of it there that you could reproduce the signal or reproduce a true signal. You could use an all pass filter, and what it would do is it would take that signal in and isolate it. Okay, it would have, here's my original signal, and then reproduce it coming out this end, but the two are not related. They would have an isolation barrier at some point, partly with this circuit, and we could reproduce that original signal without using that original signal. So the all pass filter does have applications. It's an odd little circuit, but it's very, very much so a filter, if you will. So we go through and look at them. And again, all of these filters are RLC circuits, different types. We can design them in specific ways. We set up criteria and then we go, okay, we want to have this particular circuit. And so we use the formulas and juggle it around and we get our componentry listed out and we, experiment with it, make sure that it works with these specific frequencies and there's no aberrations, if you will. But yeah, the most commons are we use the L and C componentries for them. There are other ways to make filters and whatnot, but these are the cheapest and most economical. Really, really, really. But But that's just like the introductory. We'll get more into this one after Thanksgiving. We'll go and examine this one. And like I said, I just wanted to introduce this. What we are going to talk about today. You're going to hate me so much. No, I don't think so. Let me make some proper room here. I think I can do this. Just bear with me. One good thing to know, I just signed up for through Illinois Central College. They're sending a number of us to class come December, and I'm going to have my online teacher certificate as of next semester. So from this point on, and then I can probably start looking at investing a little and getting a real camera at home. And I would probably actually even make a proper bench set up, get a nice tabletop. I have the equipment and stuff. It's just I don't really have it set up. Well, my biggest problem is the camera thing. So bear with me here. We're gonna chat about series. Basically, think of the lab of yesterday, if you will. Let's see if I can do this without there being a major. Listen, you. I think we can do this. Hold on, I'm not done. Now, let's see. Oh, what the hell? Oh, come on. We need to. What I need to do is spin this screen. Hold on here. It worked so well for me the other day. Yeah, and getting the proper tools and stuff here for me would be a huge benefit. Oh, wordy, hold on here. I don't know why it's not working. Because I have a way to, hold on. Let me see if I can, there we go. All right. I think I got this. Hopefully it comes through. All right. So, right. So, when we look at the series resonance, right? What's the first thing that we're doing? So what I want to do is basically I want to come up with this is like a limitation. My fault. The formula sheet does not cover resonance per se, so I was looking into it, and I can add on. I think I can have that by tomorrow, where I have like a series resonance formula sheet and a parallel resonance formula sheet. But because of yesterday, yeah, some of the things were confusing, if you will. So, I mean, but the key here is this, all right? And in some ways, well, yeah, we're going to do the homework for it and everything else, but let's look at it from like our technician standpoint of what the heck are we actually looking at here? And what are we trying to do? All right. So we have this RLC circuit in here. We have all three components, much like the lab that we had yesterday, right? So our biggest statement here is this, is the X of L is equal to X of C. Now, from like, yeah, I know you guys are gonna love this, but from a like a mathematical standpoint, I mean, what really is occurring here, right? That's the x of L part. And then we'll look this way. And that's what we're doing, okay? Now, if we think about this, now what actually occurs, if you will, is this way. And yeah, don't worry, I'm no, this is, it's like, what the heck? We've done all this now. But all right. So we look at a phasor diagram of this. Now, and this is where what we're doing. Oh, why am I losing focus? Look, you stupid C. Ooh, I need a better camera. I'm so sorry, boys. But so what we're doing here. Now we know what occurs on the resistor band, okay? Now we have to look at it from our signal end and what's happening. So as we swing, this way and we become more inductive, what is occurring? Okay, right? We end up where, all right, we go, let me switch colors here. And really, what is happening? So in this part of our graph, we're more inductive. And in this part of the graph, we're more capacitive and how that works. Now, from the formula here, we could see that this baby is going to be purely linear. My response is going to be a straight, smooth curve. This guy is going to be inverse. So my response is going to be somewhat of a curve gradient, if you will. Now, so when I go through and my circuit becomes more inductive, what happens is my voltage, right, the AC signal, the voltage sinusoidal is going to go out of phase with this current, and it's going to be the leading edge, okay? So the voltage, it's like big, I mean, horses at the get-go, right? And this guy is going to be the lead one out of the stall. So the voltage starts to pull ahead of the current, if you will, as we start swinging more inductive. And how much more is it going to pull ahead? Well, that would be the ratio from when we do the arctangent formula. That's that ratio. So the amount of degrees that we have, like say if we had something that's like 30 degrees, 50 degrees or something like that, that's how much more that the voltage will lead the current. Now, as we go more capacitive here, right, then what happens is the voltage ends up lagging the current. So it starts to fall behind. And by how much? Well, that would be that the arctangent, right, of this, where we would look, oh, well, that's like the x of C over R, x of L over R, our ratios. And we go, oh, well, it's by that much. So that many degrees is how much of a phase difference we start to have here. Now, what kind of impact does that have on us? Like overall, really where the biggest impact comes is this guy. All right, power. Power, if the efficiency of it. So if our power formula is related like this, right, with the current, what we end up doing here with this drastically alters this to the point where our efficiency starts to come way down. And from like a power transmission point of view, that sucks. We don't want that. It would be like an undesired effect, okay? And we wouldn't want that. So one way, like this, so if you set x of L to equal x of C, what you're doing is you're basically setting each of these to try to cancel the other out. And this would be ideally. Now, in the real world, you're never going to effectively get rid of everything. I mean, components just, they don't work that way. What we try to do is we try to get it as best as we can, as close to it as possible. Now, oh, goodness. So, an interesting thing here, gentlemen, is this. So we basically, with our first statement here, we get this. Now, what do we know? Okay. Now, if I look at this throughout, one thing I do know is this formula, and I know this formula is true. My overall impedance from this circuit can be described as this formula here, can it not? Where I would have this, our overall impedance, right? ZT, our impedance total, would be the square root of R square like that, right? So R squared plus the X of L minus the X of C squared quantity. And then overall, we do the math and we would come out with our total impedance model. Now, so what do you suppose happens when I do this though? What happens here? Now, these are exactly equal. So if they're exactly equal, say, I don't know, like any number, right? If they're 5. So 5 minus 5 is 0. And if it's 0, then what happens is this effect. Basically, they cancel each other out, and that all I have is this. Now, the interesting thing with that, when I do this for this particular circuit here, is from an Ohm's law point of view. And now, because of what I have occurring, okay, and if we look at our relation here, what can we also say? All right, and this would be like an Ohm's law point of view. So if E is equal to I times R, excuse me. All right, now R is equal to what? Or Z in this case is like so, right? Well, in this particular case, what we get is something called the maximum current. Now, it's swinging out. Normally the effect of these two, either A gives me more inductive or B gives me more capacitive. But by doing this, by stating that the X of L is equal to the X of C, and based on this formula here and how they would cancel each other out, brings us to this guy like such. All right. And then because they're equal, they cancel each other out. And this is the effect we're going through. So literally this one is canceling out this one and forcing them all to work only on this plane here. So as far as our power goes, we're at the most efficient that we can be for this particular model, but yet we still have the inductor and the capacitor in there. Interesting thing. Now, but wait, there's more. And I'm running out of room. So, I don't make paper like they used to. No. Oh, goodness. All right. So remember this. This is our model, right? Now, the next part that we're going to look at, and it's something else that we were struggling with yesterday. And again, my bad, right? Was the frequencies. So we had a few things. Let me think here for a second. Hold on. I mean, I know I'm just going, but this essentially, these are the rules that we're interested in. And I know you'll be thinking, okay, what the heck? Why are we bringing up power? And it's like, well, there is a reason for that. Alright. So, oh, hold on here. Get my pen. All right. So our next part, if you will, and because of, and again, because we're stating this, and this is basically for resonance. This is my main thing. Everything comes back to this. We're going to do other manipulations and such, but ideally everything comes back to this statement. And because of that, you know, if we did the math, right? So like from previously, and I went, okay, 2 pi FL is equal to this, we would, you know, we could basically derive, but what you end up coming up with, right, is our F of R is equal to this. And this is derived from this statement right here. So basically we pull it all out, right? To 2 pi FL is equal to 1 over 2 pi FC. And if we go through and juggle it, basically what we come up with is this formula right here. So this we know, or I hope we know, that what this does is sets my ideal resonant frequency up based on the components of my circuit, okay? And then we know at this point that Z is equal to R. We literally, by this, they cancel each other out. So our whole overall statement, so whatever our R value is in our circuit has now become what my impedance total would be. And what's the phase response on this? Zero, because it's ideal. It's going right, you know, on that graph. Because these two are canceling each other out, we're dealing on this plane only. So we alleviate this and this effect to pull us right in the middle. So now my current and my voltage are totally in phase with each other. And then we look at an interesting thing with this here. Now, based on this statement, what we can do is we look at our voltage, if you will. So because of this, another statement that we can make is that the voltage across the inductor here is equal to the voltage that'll be across the capacitor, right? And now remember, they're canceling each other out. And I have a series circuit, so my voltage drops are going to be different from component to component, right? But I have gone and set these two components to be exactly the same, so the voltage drop across to both of them are going to be exactly the same. So from a Kirchhoff's voltage law point of view, we can state this. So my voltage on the inductor is going to be equal to the voltage across the capacitor. So this way they cancel each other out. So now I can make this statement. That my voltage across my resistor, because these two are canceling each other out, that it's going to equal the full voltage supply. So whatever I have the voltage supply set to, that should be my exact magnitude across that resistor. Excuse me. I hope this is somewhat making sense. I'm leading up to something here. And then, and based on this as well, okay. And all I'm doing is equating things that we know how to manipulate. I know Ohm's law, right? You know Ohm's law. And I know my formulas for this and how I'm going to equate the two. So all of this is based on this statement right here for a resonance circuit, because of this, that I've done this, I now have this statement here for my center frequency. I can now state this. I can now state this and this and this. Now you see what's going on here, right? Because I'm setting myself up. I have a pure Ohm's law thing going on. I have my KVL covered. Okay, so as far as like my circuit rules are concerned, I have everything covered, if you will. Now, where am I going to go with this? So we still haven't done, there's two things left, right? Sort of, kind of, sort of. And so remember, everything's in phase. Now, an interesting thing, because we also use this one, don't we? So in this particular case, there's my phase response. Why is that? Remember, these two are equal. So if they're equal, and yes, Ethan, you were on the right track yesterday. Remember, we said it's in zero. 0 over R gives us 0. And the arctangent of 0 is 0. All right, I know, all right, I know. It's like, oh God. So now we have this part. So this basically, see where we're headed with this? I hope that's making sense for everybody. So we got all this going through here, right? We got the way our graph responses. Oh, hold on here. La, 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 la. So we know everything is going to be going along here. Ideal response, okay? Minimal power loss, ideal response, voltage and phase with current, bringing us down. See, because we're still dealing with an AC circuit. We're still dealing with a capacitor and inductor in my circuit, okay? So now, and we're going to observe a couple of effects here coming up. Because now we're going to go to the, well, of course, we know where we're going to go. We're going to go to the frequency point of things, right? So basically, we've got our statements, our rules, if you will, laid out for us based on this statement here. We can then state this, which we can then state this, and state that, state this, state him, and state this. Because we always, I mean, you got to figure out what current is overall, right? So that's what we have with that. And then we have this guy, right? All right. All right. So now where's our next step? Anybody guess? You're right. We're going to look at frequencies. I'm glad you guessed correctly. So now one of the things the lab did talk about yesterday was the 0.707 factor here and what we're looking at. All right. So we know we got a center frequency here, and it's, you know, dead on based on the components. So it's pretty much fixed. We'll get a specific target number. But one of the things that we know is that from a power end or transmission end, if you will, that I have some leeway on the upper and the lower sides of this frequency here, where my circuit's still going to work, not 100% efficiently, of course, but it's still going to be able to pass through with the frequency and not completely attenuate it out to the point where the voltage magnitude comes down to nothing, okay? So how do we figure out what that upper and lower end is, right? So one way to do this, and it's using, going back to our current rule, if you will. So we say the 0.707, which, right, essentially comes out to, it's like we're still operating at close to 71%. All right. Now what we're going to want to do in one vote is we look at the, oh, get out of here, spam risk. Don't want that. So what we're going to want to do is we're going to look at this as like with the voltage magnitude. All right. because we want to see when we're able to deliver the maximum voltage. And of course, the maximum voltage is when we have a frequency set right here, but we're still allowed to run through, like I say, up to still transmit through at the 70.7%. So we want to equate that with Ohm's law, right? So what we're going to do here is simply this. Get this times I, right? Current quantity squared, all right? So we're kind of using the power rule there, if you will, for my efficiency effect. So where do I get that value? Here. And this value, well, that's straight from the circuit value here. And we get that I max of the current when everything is set through like this, right? Excuse me. So we can get our upper and our lower ends, if you will, the lower cutoff frequency and the upper cutoff frequency, and get it laid out like this. Now, how does this equate? Well, I'm glad you asked. Because I am going to show you whether you like it or not. No, we're going to take a look. Let's pull up. I hate using graphs per se, because everybody interprets a graph in their own way, believe it or not. All right. So what am I putting on my graph? Oh. Yeah, right. Current versus frequency curve. All right. Of course, that's a zero mark. We'll go up, right? Higher ranges of frequencies. So what we're going to look at, let's switch. We're going to switch colors up. Oh, here's what we're going to look at, gentlemen. So if we go along here, ideally, and I'm not going to draw a number. I mean, we're not really dealing with numbers here, but I want my resonant frequency, right? And that's going to occur somewhere on this point. Now, on this point, I'm going to get my maximum power output, if you will. Okay. And bear with me. There's a reason why we're doing this like this, I guess. Now, the maximum one here is like this. All right. And this is ideal model. So ideally, I mean, it's going to be the perfect thing because we're only dealing with this, in this case of total impedance. Okay. Now, this is at this perfect resonant frequency. Now, so at a certain point, we get a 0.707 drop, if you will. Okay. And this will be the 0.707 with the current in mind, right? So 0.707 and I max, if you will, like this. So what we end up with here, all right, my lower and my upper frequencies that we're going to have from this. So, and I'm, it's not hardcore here, but we'll draw a point and a point. So our voltage magnitude is not attenuated so badly, right? What it's attenuated by is this 0.707. So we're still operating at a 70% efficiency here. So if we looked at this like this, oh, who stole my green marker? Oh, Jesus. So ideally, be something like this. All right. And so my range, if you will, uh, I'm trying to make this more color legible. So my usable area is all here, all in that, right? By this much. Now, as it starts to fall out this way, or it falls out this way, what is happening here? Okay. I mean, honestly, if you think about it, it's like, okay, so as I start to go this way, or I start to go this way, there's an effect that's occurring. And it's going to pull us down, I guess you could say, in one way. But what we have to look at is our original response, because this is not so much true anymore as we start going out into these points, right? And the reason is this starts to happen. So we're going to look at it from a current point of view and Ohm's law. So see, as we start going this way, the circuit becomes more capacitive because it's right in there, right? We got if we look at the X of C formula, 1 over 2 pi FC. So as that frequency starts to fall out, the circuit starts to become more capacitive in nature. And of course, on the other end of the coin, as start going up, what's happening here is the circuit starts to become more inductive. Now, so based on our original, right? So as we start becoming more inductive, what happens is the voltage is going to start pulling ahead of the current curve. And now my circuit's not going to be so efficient anymore. And what will happen is because of that, the voltage magnitude literally starts to fall until we get to this point, and now it's nothing. And on the other side of the coin, that's what's happening here with the on the inductive end, because this is the straight relationship in the formula, right? X of L equaling the 2 pi FL. So as we increase that frequency, our inductive reactance is going to directly increase, right? So as we decrease the frequency, of course, this one's going to become larger. So decrease, larger, increase, larger, right? And that's how we look at it this way. So decreasing the frequency makes capacitance impedance larger. Increasing the frequency makes inductive impedance larger. And I hope this is helping. See, because the book, I mean, he talks about this, but I noticed that he didn't really, wasn't really bringing the current curve into perspective, if you will. And we got one other thing to examine here, which I didn't think I was going to use that much paper, but oh my gosh. Now, so we get these set up for ourselves. We get our ranges like this, right? Now I'm interested in my quality factor. So what the hell does that mean? I mean, honestly, what does it mean? And what good does it do for me? Why would I want to know it, right? Well, all right. So a Q factor, essentially what we're going to deal with when we deal with Q factors is we've got two things to work with, right? A low Q or a high Q, all right? And what this does, and this is just something to know. It's like, okay, if I have a low Q factor circuit, it does this. If I have a high Q factor circuit, it does this. Now, what this does is it relates to my overall bandwidth, all right? Which means my regions here and here of operation. Because if I go even a little bit further with this, okay, straight down, oh God. Anyway, so from here to here is my operating regions as far as the frequency is concerned, okay? Now, Q factor, if I go with a low Q factor, is my maximum amount of room. I would have the maximum bandwidth available to me. I would have a greater range, if you will. A high Q factor brings it in and I have less of a range. So if I'm looking So basically what we would do is I'm looking for a really tight circuit that really only wants to work with this frequency and very little else, because it would be really tight on that. Then I would go for the high Q factor. Now, if I'm not as interested, or I don't mind accepting frequencies outside of what my original center frequency is, then I could go with a low Q factor and deal with that with no problem. So that's just something to equate with what we're doing here. So now, when we set our Q, we have a couple of ways to do this. And so what we can look at is how we set what Q is. And it's a ratio. And I can state this, right? Because going back to my original, X of L equals X of C. They should be the same. So either of these should give me the same result. Because if this number is the same as this number, and R is based on, the R value of the circuit, then when I go and plug either one of those in, I should be able to get my Q factor, right? Now, another way, related to this, that's my center frequency over my bandwidth. So now how do I find my bandwidth? See that? So from previous, all right, so we go through, find out my 70% efficiency. Of course, we have to have our center and find out what my peak value is here, right? Remember now, the way we're looking at this, so we look at our peak value here and get that number, all right? And then I have my center frequency, and then we do a fallout, and then we would have my lower end frequency and my upper end frequency from my center. And then we can come up with what my overall bandwidth would be then, or what my range is, okay? So I would say, oh, this circuit's capable of operating from 5 kilohertz to 15 kilohertz, and my center frequency is 10 kilohertz, that type of thing. So now if you notice, with these two ways like this, I'm able to also, if I had to, I could juggle this formula around a bit, right? And even find unknowns to the circuit if I were interested. So, I mean, one thing I could even do if I took out the Q here and just dealt with these components. So I've got 4 different values, and if I had 3 of those values, I could find the 4th one. And it's a way to cross-check as well to make sure that I'm using the correct numbers here. So it's like, well, one way I could juggle this around and find out, well, what the heck is my bandwidth altogether, right? And just juggle these numbers around and isolate the bandwidth by itself and equaling these other components, and then do the math and go, okay, that's my bandwidth. Was it what this was? No. Well, what the heck? And find out where we went wrong. So essentially, from start to finish, okay, this is what we have occurring. And this is a way to analyze a series resonant circuit. Now, why do I say series with this? Because remember now, even though we're dealing with the, the AC sinusoidal end of things, right? Excuse me. What do when we go to a parallel network, it's going to flip flop on us, right? Because this end, right, we were able to go through and able to quickly do, and everything was based around voltage change ups and getting what my current was. Now we know in a parallel network that this is going to be slightly different because of the branches. So our way of analysis varies a bit. I mean, we'll still be going through pretty much the same method, but I'd like tomorrow when we go before the lab, we're going to do a run through much like this. So we know what our rules are for a parallel resonance circuit versus the series resonance circuit. And I mean, ideally, I mean, really, when we get down to this, gentlemen, we're not doing anything new as far as the rules go. Really, what we're making is this broad statement right there and fitting it into the things I already know. Because I knew I already had this equation going on, but because I set these two to equal, we end up with this. It literally cancels out. And that's why I look at the phasor diagram so hard. And that's why I'm saying it's like, because we're making these equal like this, right? So 2 points like this, I'm plus 90, I'm negative 90. And if they're equal magnitude values, well, they cancel each other out and come to the 0 line. And then the only thing I end up with is my actual resistive element right here. And everything's on that. And so that's why I say, going back and looking at my phase shift is very much this because of this. And then because of how everything is going through, I'm able to make some broad statements here. So like my total impedance is equaling R, what my voltage effect is going to be. So you see what happens there? Because of this and they're opposites, right? Because they are on opposite ends of the spectrum. That's why you're going to have the negative VC versus the positive VL. But those two voltage drops in this circuit here, they're going to cancel each other out because one's positive, one's negative, and they're going to say, well, I'm the same as you and I'm the same as you, and boom, and we're done. Now there's still, those two elements are still there in that circuit, right? But as far as the voltage is concerned, they cancel each other out. And that way our only voltage drop we deal with is literally all across the resistor here. See that? And so that's how we go through and we can make then this statement where my VR is equal to my source voltage. And if this is the case, right, this and this leads me to this. Because if I go back to the circuit and the only voltage drop I have is him, well, guess what? Then figuring out my value of current is going to be directly on him, right? Straight with Ohm's law, where I come out and go, well, heck, then my maximum current throughout this maximum now, mind you, right? This would be a purely efficient RLC circuit where my power delivery is at its best. So the minute I start swinging this curve either way here, my power efficiency drops. And you can see by how much, right? We're talking, that's nearly a 30% drop that you're losing here. And everything else below that, and to the point where it's just purely becomes unacceptable from a power standpoint, right? Because you're not going to sit there all day long and feed something that gives you nothing in return, are you? No, that's what we have the IRS for. No, so, and that's what occurs here. So then we got our very last one. What the heck is our phase angle? And we get this. And then going through and figuring out my lower and upper ends here. Just remember, it's the 70%. And do your math and just come and plug it in. And like I say, there's my operating efficiency region, and anything else, junk. And then based on that, then we look at our final Q factor. And just remember now, this is really it's a ratio. It's a model that we could use, and it's partly, it's partly from a design standpoint. I'm not going to lie, right? I mean, why would I be interested in that? But from a design standpoint, if I were interested in, like, like I say, a real tight bandwidth, go high Q. A real broad bandwidth, or I'm not really care so much, you go low Q. And you see from that, I mean, we can go and play with the values of the components, still have the same circuit model, and change the values of the components, because I have some playroom in the values based on this. As long as I keep my frequency true, then my values of these bad boys, well, they can vary and still equal out and still come out true for the circuit. So pretty much from the get-go, you just have to decide, do you want a high Q or a low Q? Base your components on that, pick them, set yourself up, plug this through, find out what your purest efficiency model is, and then go through, do your math, and then you basically have your ideal circuit. And yes, we can plug with these formulas like this, like that. All right. And that, my friends, my young gentlemen technicians, is series resonance from my point of view. And like I said, tomorrow, and I know, I'm sorry I dragged this on. I know. I hope this was interesting. I hope it helps. But oh, let's see what I look like upside down. Oh, good Lord. Hold on. Oh no. Ah. You gotta flip it. There we go. All right. So I hope this was informative and it helped. Would you guys like a formula style sheet for resonance? Would that help you? There will be a few of these on a quiz coming up, and then the final as well.
Yes, it would.
You know, somehow I thought you were gonna say that. I truly did. So yeah, so that's what I'll do. I'll basically it'd be like an addendum to the formula sheet we already have, and then I'll go through and yeah, we'll have a series resonance one, and then we'll do the parallel resonance one, just to help with our approach, right? Just so we got the rules down. Because again, you don't want to memorize this crap. Like you got enough stuff to go into your head. As long as you're able to recognize that, I need these rules, where to go find those rules, and then how to use those rules. That's the main target here, as far as I'm concerned. But all right, well, I'll do that today then, and then yeah, when we meet tomorrow for lab, I'm gonna hand out the parallel resonance formula and then formula sheet, and then we'll have a lab for it, and hopefully we'll have a little bit better time. I mean, these are really it, and then I have one more lab planned after this, but it's more of a fun one where we're gonna hook up, like I said, we're gonna hook up those speakers and do like a little like a filtering effect, if you will, setting up some frequencies and playing around with that and seeing how a speaker, basically we're going to build a speaker driver, right, that you could then turn around and hook it up to like a radio or something like that and have your signal come in. And but that's essentially what we're going to do. But so yeah, we'll do that, and then I'll get those ready, and then tomorrow when we meet, I'll hand those out, and then hopefully we'll be able to use that with the labs and stuff, and we'll sound good?
Yep.
All right then, gentlemen, get the heck out of here and go on about your day, whatever the heck you're doing, and then I will see you boys in the morning. All right?
See you, Tom. Have a good one.
You too, man.
See you, Tom.
Bye.